Welcome to our discussion about spin 1/2 and time evolution. So we are going to take the ideas that we've discussed about time evolution of quantum systems and apply this to the spin 1/2 system. So in general, remember that we are looking at Hamiltonians that are time independent. They are equal to kinetic plus potential energy. If you're in a magnetic field, then the kinetic energy in this particular case that we're going to consider is 0 minus the the dipole moment mu dotted into the magnetic field B. So mu is the dipole moment of a particle, and due to its spin, it's going to have a dipole moment of G times the charge divided by 2 times the mass. We're going to assume that this is an electron times its spin. So for an electron, then G is approximately 2, and Q is definitely equal to minus E. So for an electron, such as, for example, the single electron, valence electron in the silver atom, then this mu becomes 2 times divided by 2, so those 2's cancel, and I get minus E over the mass of the electron times the spin here. So the Hamiltonian in this case, which is minus mu dot B, is then equal to minus mu, which is minus E over m sub E, spin, dotted into the magnetic field here. So there's a couple of things that we can do. We are going to choose the situation. We're going to pick the magnetic field to be in the Z direction. So it is equal to B naught in the Z hat direction. And we'll deal with multiple directions later, but you could just align it and say, Z direction. In that case, the Hamiltonian is going to be E over m sub E times S dotted into B. So now B is only in the Z direction, so only the Z component of the spin contributes to the Hamiltonian. So I get E over m sub E S Z times B naught. One other way of writing this is going to be E times B naught over m sub E times SZ, which is an operator. And these are all numbers. So I am going to set this equal to something which I am going to call omega naught. And this is, I am defining, so that's what the 3 lines, remember that means defined as E B naught over m sub E. This is the definition of omega naught in this section. So, okay. Because the Hamiltonian, so since the Hamiltonian is proportional to SZ, this means that H and SZ commute. This means that they share common eigenstates. So I can write now the matrix form for my Hamiltonian. Remember that here my Hamiltonian was equal to omega naught SZ, and SZ is H bar over 2 times 1, 0, 0, minus 1. So I'm going to represent it by this matrix here, which means my Hamiltonian in this particular case is being represented by H bar omega naught over 2 times the matrix 1, 0, 0, minus 1. So that's for this particular setup. Here, well, we've already solved this problem. We spent a lot of time on this problem solving it. So this means that when h is multiplied by spin up in the z direction, I am going to get, remember this is omega naught sz acting on spin up, and this gives me omega naught times plus h bar over 2 spin up. This is equal to, so remember if h is acting on a state, then it's going to give you the energy, which I'm going to call h plus, which is the energy associated with the spin up state, times that state back. So I can look at these two equations and say, E plus must be equal to h bar omega naught over 2, which is really nice. I can then look at the E minus, the spin down state. Here I have a Hamiltonian acting on spin down. I should get the energy for the spin down state times that state again. Remember that the Hamiltonian is equal to omega naught sz acting on the spin down state. And this is omega naught times minus h bar over 2. That's the eigenvalue acting on the spin down state. So this means that E minus has to be equal to this mess over here. So E minus is equal to minus h bar omega naught over 2. Those are my two setups. I have my minus signs, and it also means that the eigenstate E minus, so the eigenstate associated with this particular eigenvalue, is the same as the spin down in the z direction, which is particularly helpful. So let us start by considering a general state, initial state. So let's consider spin up in the in hat direction. So this is some direction that has some angle theta and some angle phi in the xy plane. And we, remember, can write this general state. This would be spin up in the in hat direction. This is equal to the cosine theta over 2 spin up plus the sine of theta over 2 e to the I phi spin down, which I can represent in matrix notation as the cosine of theta over 2 times the sine of theta over 2 times e to the I phi. It doesn't matter if you put the I phi, e to the I phi behind the sine of theta over 2, in front of it, whichever makes you happy. So what we're going to do in class is we are going to derive the Lamour frequency by taking this initial state. We will then, we've already found the energy eigenstates, which is step 1. So we'll start in with step 2, which is finding the state as a function of time. So we have to write it in terms of the energy eigenstates, which we've already done. So then we find here, we have it in terms of the energy eigenstates. And then 3, we include this e to the minus I times the energy of whatever particular state it is, t over h bar. We include these factors. And then we will look at 4. Our ultimate goal is to find the expectation value of the spin, which we will be able to do by, what happened to my list? Which you can do by finding then the expectation value of Sx in the x hat direction, plus the expectation value of Sy in the y hat direction, plus the expectation value of Sz in the z hat direction. And don't forget that the value of Sx can be given by the psi of t, and then put the operator in the middle, and then act on the ket here. Of course, there will be further instructions in class. So I will see you then.